Okay, so this little video is about orthogonality. Okay, so we know essentially from linear algebra what it means for things to be orthogonal, right? A vector in two space, are orthogonal if they're 90 degrees apart. Well, we're going to extend this notion of orthogonality to more general inner product spaces, so function spaces, sequence spaces, image spaces, etc. All right, so if I have two vectors in my inner product space, x and y, then I can define the angle between these vectors, x and y, as the, using this particular formula. So in other words, I can write the inner product of x with y is the norm of x, norm of y, cosine theta. Now this really comes from the Cauchy-Schwarz inequality. Remember, Cauchy-Schwarz says the absolute value of x with y is less than or equal to norm of x, norm of y. So what we're doing here is we're saying, well, okay, we're going to get rid of the absolute value. So on the left-hand side, this thing can be positive or negative. So the inner product of x and y is going to be positive or negative, and we're going to have that equal to norm of x, norm of y, times a fudge factor, right? Some fudge factor alpha. And that fudge factor alpha can be positive or negative, but the fact that it's less than or equal here means that fudge factor is going to be between plus or minus 1. All right, so if this alpha is between plus and minus 1, alpha is in plus or minus 1, then we can define alpha to be, we can actually define alpha to be cosine, let alpha equal cosine of theta. And now we can think of, because cosine of theta is obviously between 0 and 1, and now we can think of theta as the angle between these two vectors. All right, so this guy really comes from the Cauchy-Schwarz inequality. And this is really an important formula. In two space, we have, here might be x, and this might be y. And we're going to say that, basically the inner product between x and y is going to be equal to the length here of x, the length of y, times this angle theta between the vector. Okay, so again, if you have two functions, I have a function like this. This would be x of t and y of t. Again, I can define the angle between x of t and y of t using this formula. It doesn't quite, look like this, but the formula works just as well. All right, so now we can start talking about vectors that are collinear. And again, when I say vector, I might mean a function or something in a vector space, a function, an image. All right, so I have two vectors, x and y and x. We say that those vectors are collinear if the angle is 180 degrees times n. So in other words, in R2, of course, our kind of intuitive picture says that x and y are collinear if the angle between them is 0 or 180 or etc. And then we say that two vectors are orthogonal if it's 90. So again, in R2, we have this intuitive notion where we need a 90-degree angle between x and y for two things to be orthogonal. But again, this is for general vector spaces. So in other words, if the inner product is equal to 0, by the way, back here, when something is collinear, then we have that the inner product of x with y, absolute value, is equal to the norm of x, norm of y. This is collinear. And for orthogonal, we have that the inner product of x with y is equal to 0. And we say that if the inner product of x and y, if the inner product of x and y is equal to 0, sometimes we'll write x is orthogonal to y. All right, and just to sort of emphasize the point, if we have, for example, the functions sine of t and cosine of t are orthogonal on this space L2, 0 to 2 pi. So if we take the inner product of x with y, which would be, in other words, this thing is omega. So we have, it's going to be the integral, the inner product is going to be the integral from 0 to 2 pi of sine of t cosine of t. And this guy is equal to 0. You know, remember on 0 to 2 pi, you know, sine looks like that, cosine looks like that, and if we multiply these together and sum everything up, we get that these guys are equal to 0. We could also look at the following vectors in, say, L2. Okay, so we have a vector that's 1 for the first 4 and zeros, and then, well, I guess this isn't necessarily an L2, but plus or minus 1. If we take the inner product of these two, we'll get, you know, 1, minus 1, 1, minus 1, and then zeros. And so the inner product is going to be equal to 0. So we can take inner products of, you know, any vectors in vector spaces. We can take the inner product when they're equal to 0. Those two vectors are actually orthogonal to 0. All right, let's see. These slides are a little bit out of place. I think I'll move them to be closer to when we talk about inner products, but I just wanted to give some more examples of valid inner products. Okay, and this is an important concept in of itself, this notion of matrix positive definiteness. Okay, so we say a matrix W, this is a square matrix, Rk to Rk. This matrix is positive definite if for every x, x transpose Wx is greater than 0. And actually, we can extend this to complex numbers. So if W maps complex k to complex k, then we say it's positive definite if x Hermitian Wx is greater than 0 for every x in complex space k. Okay, so this notion of positive definite converts over to complex matrices as well. And then we say that the matrix is positive semi-definite if x transpose Wx is greater than or equal to 0. Negative definite if x transpose Wx is less than 0 for every x, or negative semi-definite if it's less than or equal to 0. And if it's none of these things, then we say that the matrix is indefinite. And actually, I believe here that I need the requirement that W is equal to W transpose. Or in the complex case, we would have W equal to W Hermitian. So this is positive definite is only defined on symmetric matrices. All right, so for example, this matrix W equals, the identity. It's positive definite because x transpose Wx is just x1 squared, x2 squared. Actually, I could put a positive alpha beta in here, and this would be alpha beta, as long as alpha and beta are positive. That's an example of a positive definite matrix. There's others that don't necessarily have to be square. This matrix, 1, 0, 0, is positive semi-definite because when I do x transpose Wx, I just get x1 squared. And this is going to be 0 for every x, x1 is 0, but x2 does not have to be 0. Alpha can be real. And then, an example of an indefinite matrix would be something like this, where x transpose Wx is this guy, and it can be positive or negative depending on how we pick x. All right, so if I have a weighting matrix W, then I can define a weighted inner product. So the inner product of X with Y, weighted by W, I guess, would be X Hermitian WY. This is a valid it'll satisfy all of the properties of an inner product, and it has an induced norm. And the induced norm, is this guy, and we will often write the induced norm with this W down here. So this is the induced norm. We can also do weightings, weighted inner products of functions. So for example, if I have some function that's positive definite, in other words, it's always positive, then I can take the inner product and weight it with W. And this gives me a valid inner product. In fact, expectation can be thought of as exactly this. The weighting function is going to be the probability density function. So the probability density function times X times Y integrated over its domain, and this inner product is, this is the inner product of any two random variables. So that's another example of an inner product. I'm not going to say a lot about random variables. A lot of you are taking ECE 670, but this class 670 is not a prerequisite for 671, so I'm not going to do a lot of stochastic processes or random variables. Okay, here's another example of an inner product. Let IM be the set of all grayscale images with m by n pixels. So if you look at if you take 640 by 480 grayscale images, every possible image that's out there in the world, you let that be IMN. And they're grayscale, meaning each of the pixels has an integer value between 0 and 255. Turns out this is a vector. Well, actually, you have to allow 0 to 255, not necessarily integer values, for this to be a vector space. If you do that, then an inner product can be defined as just simply, summing over. You take two images, you multiply them together, and then take the sum of all of those elements, and that is a valid inner product. Okay, I'm going to stop here.